Hello, this is Dr. Ruby, and welcome to the first lecture for Module 6, Determining the Force of a Muscle Contraction. On the next two slides, please review the objectives for section 14.1. Again, use these objectives as tips to study for the quiz. Remember that if you see a term that you do not understand in the reading, take the time to look it up either in your textbook or on the Evolve website so that you will understand that term when it comes time for the quiz. Partial contraction of a muscle. There is a hierarchy of motor unit recruitment. In a weak contraction, there is a small motor unit recruitment. In a stronger contraction, there's an increasingly larger amount of motor units in addition to smaller motor units. This hierarchy is known as the Henneman size principle. Generally, smaller motor units are innervated by smaller motor neurons and contain red, slow-twitch muscle fibers. If every motor unit of a muscle contracts, the muscle contracts at 100% of its strength. If only some motor units contract, the muscle will have a partial contraction. The number of motor units that contract and also the number of muscle fibers in those motor units determines the degree of a partial contraction. Muscle fiber architecture. This is the structure of the muscle. So in longitudinal muscles, the fibers run longitudinally. There are several categories of longitudinal muscles. There's fusiform, strap, rectangular, rhomboidal, triangular, and sphincter. Longitudinal muscles are classified according to their shape, so all of these names are related to the shape of the muscle. A in this diagram represents a fusiform shaped muscle. B is a strap muscle. C is a rectangular shaped muscle. D is a rhomboidal shaped muscle, while on the right, E is a triangular shaped muscle. Sometimes triangular muscles are referred to as fan-shaped muscles. There are also architecture descriptions called pennate muscles. In pennate muscles, the fibers are arranged in a feather-like manner. There are three types of pennate muscles: unipennate muscles, bipennate muscles, and multipennate muscles. The word pennate itself means feather-like, and the various prefixes refer to the placement of fibers along the tendon. Figure A is a unipennate muscle, Figure B is a bipennate muscle, and Figure C is a multipennate muscle. This slide tells some facts about muscle fiber architecture. Longitudinal muscles have long muscle fibers, where pennate muscles have short muscle fibers. But pennate muscles have more muscle fibers than longitudinal muscles. The fibers of longitudinal muscles are oriented along the length of the muscle, where the fibers of pennate muscles are oriented at oblique angles to the length of the muscle. If a pennate and longitudinal muscle of the same overall size are compared, they will contain the same mass of muscle tissue. Active tension versus passive tension. Active tension is generated by a sliding filament mechanism. For example, its contraction. Passive tension is created by fascia of the muscle. Total tension is active and passive tension combined. In this situation, it may help to think of passive tension as a rubber band. When a rubber band is stretched, it's naturally elastic, and it creates a pulling force that will pull on whatever is holding the band in the stretch position. On this slide, please review the objectives for section 14.2. On this slide, there are additional objectives. And two more objectives. Let's discuss the concept of active insufficiency. What happens when a muscle's number of cross bridges decreases? Well, if the number of cross bridges decreases, the strength of the muscle's contraction decreases. One of the best examples of active insufficiency can be found in the extrinsic finger flexor muscles of the arm or the forearm. We will describe this in a few moments. First, let's look at the diagrams. Diagram A shows a shortened sarcomere and B shows a sarcomere at resting length. Note that the inaccessible binding sites result in fewer myosin-actin cross-bridges being able to form when the sarcomere is shortened. This results in a weaker contraction. This illustration shows a lengthened sarcomere. Note the fact that the inaccessible binding sites result in fewer myosin-actin cross-bridges being able to form when the sarcomere is lengthened. Now let's look at the example from the wrist. Why are these wrist positions weak? The photograph on the left shows shortened active insufficiency, and on the right shows lengthened active insufficiency. Why is this position stronger than the previous two? In this position, the hand is in a neutral position, allowing for maximum contraction because of the greater number of myosin-actin cross-bridges in the sarcomeres. Now let's look at the concept of a length-tension relationship curve. The length-tension relationship curve compares the length of a sarcomere with the percentage of maximal contraction that the sarcomere can generate. Because a muscle is composed of many sarcomeres, the relationship between the tension and the length of a sarcomere can be extrapolated to the relationship between the length and tension of an entire muscle. The passive tension when the sarcomere is at resting length is non-existent, or zero. When a working muscle is at a much lengthened state, it is dangerous. It can lead to tearing or disruption of a muscle tissue. There's lessened active tension when a muscle is shortened. This is shortened active insufficiency. When a muscle is lengthened, there's lengthened active insufficiency. This is an illustration of the force-velocity relationship curve. This curve correlates the tension force that a muscle can develop relative to its velocity of contraction. Concentric contraction is shown on the right, eccentric contraction on the left. Regarding concentric contraction, the slower a muscle contracts, the stronger its contraction force. The faster a muscle contracts, the weaker its contraction force. Leverage of a muscle. Leverage is the mechanical advantage that a force can have when moving an object. Leverage is an extrinsic factor. Internal forces are generated internally from within the body. External forces are created externally outside of the body. Gravity is the most common external force. Examples of external forces other than the force due to gravity that are encountered when exercising include spring forces, forces due to resistance tubing, and forces due to therabands. A lever is a rigid bar that can move. Movement occurs at an axis of motion. The distance from the axis to the point of application of force is the lever arm. This is sometimes referred to as a moment arm or effort arm. The longer the lever arm, the less effort it takes to move the lever. There is a mechanical advantage, the advantage of being able to move heavy objects with less effort. The picture on the left of this slide shows a simple lever. In the picture on the right, how are the two people who have such different weights able to balance on the seesaw in the illustration? The answer is leverage. The 100-pound person's weight has the mechanical advantage of the longer lever arm. Bones are levers. Muscles create forces to move bones. Joints are the axis of the motion. Muscle B in this figure has a greater leverage because it's taking the advantage of a longer lever arm. Please review the objectives on this slide for Lesson 14.3. Here are additional objectives for Lesson 14.3. Now let's discuss the leverage of a muscle in more detail. We must also consider the angle of the pull. The optimal angle of pull is perpendicular to the long axis of its bone. If the angle is oblique, not all the force will go toward moving the bone. A 90-degree angle is described as perpendicular, and it is also known as a right angle. Simple trigonometry can figure out what percentage of a muscle's pulling force contributes to the motion that is occurring. Whatever portion of a muscle's line of pull does not contribute to motion at the joint, instead contributes to stability of the joint by pulling the bone along its axis into the joint. In this illustration, the 86% of the muscle's pulling force that is lost due to motion is valuable because it adds to the stability of the joint, protecting the joint from injury. A musculoskeletal lever arm is the shortest distance from the center of the joint to the line of pull of the muscle. The previous definition did not account for the angle of a muscle's pull, hence the need for this refinement. Which muscle, the one on the left or the one on the right, has a longer lever arm? The muscle on the right in Figure B has a longer lever arm. Classes of levers. There are 3 classes: first, second, and third class. The difference between these classes is the relative location of the application of force to cause movement, and the force of resistance to movement relative to the axis of motion. The resistance to movement would be whatever force resists the motion from occurring. Let's categorize these levers. From top to bottom, there's a first-class lever, a second-class lever, and a third-class lever. First-class levers involve F and R on opposite sides of A. The extensor musculature acting on the head is an example of a first-class lever. A second-class lever is F and R on the same side of A, and F is farther from A. The toes provide the axis of motion for this action at the metatarsophalangeal joints. A third-class lever, F and R on the same side of A, and R is farther from A. The brachialis is a third-class lever. It has less leverage, but the advantage of less leverage is that it gains the ability to move the forearm quickly through its range of motion. Muscles often are at mechanical disadvantage when working against a force with greater leverage. This is the resistance force. Needing to generate contraction strength when the muscle is at a mechanical disadvantage increases the risk of a muscular strain. Leverage of resistance forces. What is the resistance force in this picture? The weight of the hand and the forearm are the resistance force. You can see it in Figure A and in Figure B. Which of these is the safest method for lifting a heavy object? A, B, or C? The squat bend with the trunk remaining vertical is the safest method for lifting the heavy object. C. This concludes our lecture for the first part of Module 6.